Now we're going to see how the forest, the decision forest or the random forest is built. So the last time we have seen an example with a data set of geometrical figures such as triangles and squares, and we wanted to determine the class of what makes a figure be a triangle and what makes the figure be a square. So we started building the decision tree by choosing one attribute. So this is here we have all the objects. And we chose one attribute, for example, the color, to split the tree based on that attribute. This means the tree will have 3 branches because this attribute has 3 values. It has yellow color, green color, and red color. We have chosen this, just to review what we've done in the previous lecture. We have chosen this color attribute by doing a calculation of what is the best attribute to choose. We have calculated the information gain, that is a measure that's used in information theory, to determine the most pure split. This means the attribute that's going to give us the highest information gain. So we have some information gain minus a residual information, which is residue or impurity. And we're going to calculate this impurity. We want to minimize the impurity as it is subtracted from the overall information gain so that we get the highest information gain. So we will compute the information gain for each of the attributes that we have. So in this particular table, we had 3 attributes: color, outline, and dot. And then in the last column of this table, this decision information system table, is the class attribute. So the class attribute is shape, and its values or class labels are triangle and square. So our task here, our purpose, is to determine what makes the class be a triangle, what makes it to be a square. What we did is we calculated probability of having a triangle is 5/14 because there are 14 objects altogether, and 5 of those objects are triangles. The same for the squares. 9 of the objects are squares out of the 14 objects. So 9/14 would be the probability for having a square class. And from there on, we computed the information gain for each of the attributes. And we determined that the attribute with highest information gain is the color. So it gives us 0.24, while the others gave us 0.1 and 0.04. So therefore, we have chosen the color as the most informative attribute. That was our heuristic information. We choose the information with the highest. We choose the attribute that gives us the highest information gain. So that is the color. So once we've chosen the color, we end up with 3 subtrees, each of them in its own color. The yellow ones are here, and we have a leaf because all of those are of the same class label, squares. Over here we have the green objects, and here we have the red objects. So we then, on the yellow part, we're done because we have a leaf. Now the green and the red ones, we said we need to continue splitting them. So to determine if the class is a triangle or a square, because those have these triangles and squares mixed up in here. We have already used the color attribute. There are 2 attributes remaining to choose from: the outline and the dot. So we will compute information gain for each subtree for the outline and the dot. With the green subtree, the outline gives us the higher information gain. So we choose that one and we end up with a leaf and another leaf. This means all the objects are square, all the objects are triangles. So we can answer the question here. If the color is yellow, then you have a square. If the color is green and the outline is solid, then you have a square. If the color is green and the outline is dashed, then we have a triangle. For the red objects, we're going to do the exact same thing. We will calculate highest information gain for remaining attributes, and that is the dot here. So no dot makes the class be a square. It means all the squares don't have any dots in them, while the triangles have this little dot right here. You can see on the bottom of the triangle. So yes, we have a dot. It means if the color is red and we have a dot, yes, then the class is a triangle. If the color is red and no, we do not have a dot, then the class is a square. So we end up building this very beautiful tree that you see here, which is what we wanted to do. This means there are several or a number of trees possible. We wanted to build the best one that answers our question as quickly as possible with as fewest questions as possible to be able to reach the leaves, which are these yellow rectangles here. That is where our knowledge is at. So this tree is level depth 2. By answering 2 questions, we can get to the knowledge. That is what we wanted to do because we have seen earlier that depending on what attribute we choose, we could end up with a different tree for the exact same data. Like this is the kind of tree we want to have, but we could end up with something like that if we choose the incorrect attribute to split the tree. This incorrect, by incorrect we mean that we will produce a huge tree that's many levels deep, that's more complex to compute, takes more space in memory to store it, and takes longer processing time to traverse it to obtain the results. So that's why we compute those measures, so that information theory, information gain, so that we can get the best, easiest, quickest tree. And that is what we obtained over here for the triangles and the squares. We wanted to see some real life decision trees and then some decision forests. Here's a decision tree that tells if a customer will redeem a coupon, and this tree was built with a commercial software such as Cart or C5. So this tree tells us that if we traverse the tree, if the customer is loyal and the household income is bigger than 150,000 and he shops in store, then he's going to redeem the coupon. Yes. So the class here is, will he redeem the coupon or not? We have seen earlier the tree has roots, it has nodes and branches, and at the leaves of the tree is the knowledge or the class label that we would like to reach. It's possible to have a regression tree or a classification tree. The regression tree is going to do a linear prediction of a value, while the classification tree will predict the class label. It is possible to have binary features. If that's the case, then the tree will be a binary tree. That is, it will have 2 branches only. We mentioned we want to have a tree that is as shallow as possible. A tree of depth 1 will be the best case scenario. This means that with answering 1 question, we are able to get to the answer. So, number of inner nodes 1, number of terminal nodes 2 for this tree. This is a much bigger tree of depth 3. That's what we're looking to avoid, much deeper trees, because it will be more difficult or more complex for us, as we can see on the visualization, to obtain the answers. Here is a really huge complex tree of depth 20 that, as you can see here on the visualization, would really take a long processing time and answering almost 20 questions in order to obtain our answer. We will see here an example with a classical machine learning data set called the iris data. Iris data is a data set of flowers. There are 3 classes for the iris flower, depending on the petals size and length and width. There are flowers that have their petals are round shape, like this iris setosa right here. They are more round and bigger. And then for the iris virginica that's over here, they're more elongated, and overall size they're smaller. So this flower is bigger than that flower, and this flower has more round petals, while this one has more elongated petals. So there's actually 3 classes. We have iris setosa, iris virginica, and one other one. And based on the petal length and petal width, we would like to determine the class of the flower. Is it iris setosa or iris virginica? If we are to map this tree, if we're going to build just a simple decision tree here, by hand, just by looking at this is a small subset of the original iris data. We can build a tree just by hand, by, let's say, pick the first attribute to be split the tree first. That's going to be our root, the petal length. If the petal length is less than 3, then we have an iris setosa. You can see this in the first 3 objects. These 3 objects, their petal length is 1.4, 1.5, 1.3. This means we have an iris setosa. Now, the object number 4 and 5, their petal length is 6 and 5.1, which means their petal length is bigger than 3. Then we have an iris virginica. Now, if we build our tree or our model, our classifier, by using the data in this small table here, when the new data comes in, let's say we have this flower right here that our tree has not seen before. So the tree does not include this flower in its original training to build this model. That's a new data item that did not exist in the training data. This is a testing data item. So this testing data here says what kind of flower is this? We would like to know what kind of flower is this. This ruby red flower with the yellow in the middle here. Is this an iris setosa or an iris virginica? So the question is, what, as you can see this red question mark right here, what kind of flower is this? Well, we're just going to traverse our tree from top to bottom, and we will answer the questions. Is the petal length less than 3? No, the petal length is 5.1. So it's bigger than 3. Therefore, we have an iris virginica. So the class of this new flower, ruby red flower here with the yellow in the middle, is an iris virginica. So what we are seeing here, we have seen this deep tree with depth 20, and then we have seen the iris dataset scatter plot. So this is a visualization of the iris dataset. Well, we have the petal length on the bottom axis, on the x-axis, and the petal width on the y-axis. So we are plotting a scatter plot. Each flower is presented as a dot on this visualization, a data item based on the value of its length, of the petal length, and the petal width. So this flower right here, for example, on the bottom left corner, the red one has a petal length 2.5 and a petal width of 2.3, and that's why this particular flower is visualized in this location, because we have 2.5 value for x and 2.3 value for y. So what we can see here is the red color or red-orange color flowers on the top left of the visualization, and these are the Iris setosa. The Iris virginica are the blue ones onto the right side, which means you can see that their length of their petal is much bigger. That's why they're on towards visualized towards the right side of the coordinate system. These Iris setosa are the smaller flowers. They're visualized towards the left side of the coordinate system. And we actually have a third class called versicolored, which are the green ones that are right in the middle. They're in between those, the other two classes. This is another visualization of the iris data right here. So we have an Iris setosa, orange ones, Iris virginica, is shown in green color, and versicolor is shown in gray here. So what you can see here is the decision tree that was built from these iris data set by using a commercial software such as C5 or CAT software. We just feed the data into the software, the data mining software, and ask it to build a classification tree for us. And by traversing the tree, it's the exact same thing as the manual tree we have built, starting from the length of the petal. This particular tree says if length is less than 5.5, we have an Iris virginica. If it is bigger than that, we have an Iris setosa. From there on, we use the petal width, and if it's bigger than 2.8, we have the Iris versicolor. So that is on the right side. If it's less than 5.5 the length, we have Iris virginica, and if the width is less than 6.2, we have a versicolor. So that is how, by traversing this tree, we can determine the class of the flower. Okay, so we would like to minimize the depth of the tree and the size of the tree. We have talked about underfitting and overfitting in week 1 and week 2 discussions. We would like to minimize overfitting here. We will stop splitting the tree after a certain depth. This means we can decide how deep our tree is going to be. And if it gets bigger than that, deeper, then we stop. So maximum depth is 15 here. Once we reach this depth, we will finish the tree and stop splitting it. We can also choose the minimum node size. If we would obtain a subtree with a particular number of objects in it, we can stop splitting the tree. Means the subtree we obtained is too small for further splitting, then we will stop. So that is how we would minimize the overfitting. So strengths and weaknesses of the decision tree, and the decision tree ensembles that we have for our subject today is going to help us address the weaknesses of a single tree. So the weaknesses of a single tree can be addressed by having a decision tree ensemble or a random forest or decision forest. So the strengths of the tree is that the small trees are easy to interpret and scale well to a large number of objects in our database. They can handle data of all types. So the data requires little and very little pre-processing. We could do automatic feature selection or attribute selection. If there's missing data, this particular machine learning model is okay with the missing data. It can handle it. And it is a non-parametric model. These are its strengths. The weaknesses is when the tree is too big or too deep, it's difficult to traverse, right? It takes a long time to find the answer. We have to ask too many questions to reach the knowledge or the leaves. And then it's computationally expensive. That is, it takes a it takes a long time to process to build the tree. It takes lots of resources such as memory and CPU time. All the splits depend on previous splits. So this is an additive model. Trees are step functions. That is, we have binary splits. When there is a single tree, it is possible that the tree's accuracy is small compared to when we have a number of trees working together in a forest or in an ensemble. That's why the decision tree ensemble or decision forest, random forest, is going to help us to improve the accuracy of the decision tree classifier. The single trees have high variance. So once again, the decision forest, random forest, or decision tree ensemble will help us to improve the variance of what a single tree would give us. So how are we going to build the decision tree ensemble or random forest? Here's the original data. We're going to divide the data by random. So we will take bootstrap sample 1, bootstrap sample 2, bootstrap sample 3, and so on up to n samples. From each random piece of data, we will build one tree. So we have tree 1, tree 2, tree 3, and up to tree number n. Each tree is going to produce a result or compute a regression variable or a classification class variable. Once the trees are done with its computation, single trees, we will move to compute the average, that is the results from each of those three, and to produce a single result, because currently with this fourth or ensemble, we will end up with tree 1 has one result, tree 2 has another result, tree 3 has another result, tree n has yet another result. We want to take all of the results from each one of these trees, combine them into a single result. Well, how are we going to do this? As we mentioned earlier, there is several approaches. One is to have take the average, what is shown here, of the results. Another one is take decision table majority. This means these are trees. Each tree is going to vote for whatever result it obtained, and what the majority vote is, that's what we will give as the answer. Another option is for us to write code of our choice into this reducing phase here that combines the results. If, let's say, we're using a MapReduce here for big data, where the reason we split the data like this is because it's too big for a single tree or for a single machine to even attempt to compute a tree from this kind of data. So we split it into small pieces and give each piece to a separate machine or a mapper to compute the decision tree based on that piece of the data. So each mapper is going to compute one tree and produce a result. Then into the reducer phase, we can take the average, majority table vote, or we can take code of our choice. We can write here and the reducer function our code of what we would like this this reducer to do. This means what we would like, how we would like to combine the results from each tree in our random forest or decision forest. What this picture is showing here is Bootstrap. Bootstrap is a sampling process of selecting a subset of items from a large collection of items. Bootstrap sampling with replacement, it means that a data point drawn in a sample can reappear in the future in other samples. So there's two ways to do this. For big data, we're going to take specific parts of the data and give it to one machine. The other machine will have different part of the data that is not overlapping with the first one. Now, if the data is smaller and we're just doing this on a single machine, that we can have those samples overlap and be completely random. Then we will fit the overgrown tree into each sample set and finally take the average. So, what is bagging? Bagging is a bootstrap aggregation or wisdom of the crowd. So as we said, we can have each tree do a vote and take a majority table vote. So wisdom of the crowd, we will take the result of all the trees and their vote or their average. So that's called bagging or bootstrap aggregating. Here's the random forest. We're going to take each data sample by random by taking a random piece of the original data. That's why it's called a random forest. And each tree into the forest, we will build, from each random piece of data, we will build a tree. So we have tree 1, tree 2, tree 3, tree up to tree n. So the random forest is identified as a collection of decision trees or a decision tree ensemble. Each tree estimates classification, that is, it is voting. Its classification within the random forest will be called a vote. So we will consider each vote from every tree and choose the most voted classification. This is called majority voting. So whatever class most of the trees are recommending, that's the class that we will present as the final result from using a random forest versus a single tree. So the random forest will follow sample bagging process as the decision trees, but each time a split is to be performed, the search for the split variable is limited to a random subset M of the P attribute. This means a random subset of attributes, variables or features. So attributes are also called variables or features. So this is our split attribute. This means this is the, as you can see, originally when we were building this decision tree, we had to compute the information gain, and we were using the entropy to compute the information gain. We can randomize we can do split attribute randomization. This means we will randomly create a subset of attributes from which to choose for the split. So from those random set of attributes, we will choose the most informative attribute to split the tree and their subsequent subtrees. So, what is the advantage of bagging and versus random forest? So, if we are to compare these two methods, which one is better? What is their advantages and disadvantages? Bagging introduces randomness into the rows of the data, while random forest introduces randomness into the rows and the columns of the data. Combined, this provides a more diverse set of trees that usually lowers the prediction error, which means it is more accurate. So by combining these two approaches to build our tree ensemble or random forest, along with bagging, we would accomplish a higher classification accuracy. If we are having a big data, this means large enough N, about 63% of the original records will end up in a bootstrap sample and 36% are not used. This means for the training purpose, for building the trees or the classifiers, but those will be used for testing to determine the accuracy of the overall decision forest or decision tree ensemble classifier. So these observations are considered out of bag and can be used for efficient assessment of the model. This means for testing. We can do a cross-validation, or if it is unstructured data, we can do our testing with these remaining 40% of the samples. This is just for big data. When the number of the data samples is smaller, this is not necessary or it is not that efficient. So, random forest or decision tree ensemble, if we would like to fine-tune this algorithm, it's a good out-of-the-bag performance, but there are a few parameters that can be tuned. What parameters can we tune? For example, the number of trees. How many trees we would like to have in our forest or in our decision tree ensemble. So choosing this number would typically have the largest impact on the predictive accuracy. We can choose the node size. This means once we split the data into subtrees, how many data items are within the particular subtree that we obtained. We can play with that number and tweak it, make it smaller or bigger. We can choose that number. It will have some effect on the predictive accuracy, and it might also increase the computational efficiency. We could have certain rule for how we would split. So when we were computing this entropy measure, that's pretty much a rule on how we split if we choose the attribute with the highest information gain out of all of the available attributes. So we moved towards a decision tree ensemble or forest of trees because we wanted to improve the accuracy of the decision tree classifier. So the strength of having a decision tree ensemble or a random forest would be competitive performance. It is good out of the box algorithm. This means very little tuning, fine tuning, is required. It has a built-in validation set. We don't need to set aside additional data for validation. There is little overfitting. It handles outliers very well. It handles missing data. Automatic feature selection is provided, and a minimal preprocessing. So these strengths, these are quite substantial strengths compared to the single decision tree. How about the weaknesses? Although accurate, if we use advanced boosting algorithms, then the accuracy will be even better. If the data is too large, the processing of the decision tree ensemble or random forest can become slower and less interpretable. That is, the more data we have, the more difficult it will be to interpret the results because we will get a large number of results and we need some post-processing method in order to decide which results to present to the user. So we always want to present to the user the essence or the most important, the best results. Okay, so we have seen earlier already this. This is the iris dataset. The Iris setosa flower, the bigger flower, is round petals. Iris virginica is a smaller flower with elongated petals. Once we build our model, when a new flower comes in, we can determine the class of the new flower. As we mentioned, we can build this kind of a dataset, this decision tree by hand. We can just draw it on paper over here based on a small data sample we are showing. Another way to build the tree is by using data mining software such as CART C5 or an Orange software. This Orange is a free machine learning data mining software that we can download from this website. And for the Iris dataset, here is the decision tree that the Orange software creates. So, by using the petal length, we split the original data. If less than 1.9, we have an iris setosa. Bigger than 1.9, we have an iris versicolor. Next, the petal width is chosen. Petal width is less than 1.7. We have iris versicolor. If it is bigger than 4.9, we have an iris virginica. Is bigger than 1.7. We also have an iris virginica. And then we use the petal width again. If it's less than 1.5, we have iris virginica. Is bigger than 1.5, and iris versicolor. So this particular tree was built by the Orange machine learning software. We could code the decision tree ourselves from scratch. Here is some code, for example, that is coding the decision tree. Or we can use the Python libraries that we are using here in our textbook. For the Python libraries, the decision tree already exists. That is, we could call a random forest class, a random forest, and from there get a decision tree for ourselves. There isn't a decision tree class on its own, but only the forest is available in the Python libraries. Here is some big data code that is using Scala language and Spark machine learning library for big data processing. Over here, we can see the same thing as with the Python libraries. As a matter of fact, we can use the Python language for Spark if we would like to. It supports Python as well. So we would call the random forest.train classifier in order to train a classifier, and then we would test the classifier with the remaining data. Okay, so let's see right now. We will continue with our Google Collaboratory with the Google Collaboratory with the Jupyter Notebooks for using Python, Skylern, and Keras libraries to build the decision tree and the random forest. Okay, so let's look at